All right, so today we're going to look at some other ways to talk about 3D coordinates and look at equations in 3 dimensions. Uh, we've been working with rectangular coordinates where we have an x coordinate, a y coordinate, and a z coordinate. Today we're going to introduce two new systems, and these will be helpful when you get into volumes and into triple integrals and farther down the line in your calculus career. So our cylindrical coordinates, we have, instead of x, y, and z, we are going to go polar instead of x and y. So we're going to have r theta, and then we will have z, and that will stay in common. And then when we go spherical, we're going to have this symbol called rho, and then we're going to have theta, and then we're going to have a new um, angle called phi or phi, I think, depending. We'll call it phi. So here we go. Our cylindrical coordinates come from basically creating this cylinder. So instead of x and y, we are replacing it with the polar coordinates of r and theta. And this looks fairly complicated, but as you can see, if you just think about the xy plane down here, right? There's my xy plane, which is flat. Here's the x coordinate is right here. Here's your y coordinate is right here. And then we have our r, which is this, and our theta is the angle going from the x, the positive x, towards the positive y. So that's very similar if you think about taking our xy plane and laying it flat. So that comes there, and then our z is our height. It's the distance from the point to the xy plane. So z is the distance from the point to the xy plane. So down here we're going to have our radius is r, our angle is still theta, and then our z would be 0. And up here at this point we have r theta z for some given thing. So we're going to kind of use those things. Here's another picture that's maybe a little bit easier to think about. So here's again, on the bottom is our xy plane right here, right? And our theta goes from the positive x towards the positive y. Just like here, this is my positive x, here's my positive y, and we measure theta moving that direction. And in that system, right, here's x, here's y, here's r, and it's very similar. I have x and I have y and I have r, and we have our r and we have our z. And so again, just like in polar, x is r cosine theta, and y, because our theta, if you imagine this picture, is right down there, so cosine theta is x, sine is x over r, sine of theta is y over r, and x is r cosine theta. And our z is going to stay our z, so there will be a common point in going from rectangular to polar, or to cylindrical, which is sort of the polar of the 3D world, if you will. And again, same as in polar, our radius is the square root of x squared plus y squared, because r squared is x squared plus y squared. It comes from that. This is still a right triangle if you imagine this triangle on the base. So if you think about, actually we'd be coming more like, like this. Yeah. We still have a right triangle between the x and the y and the r. So theta is inverse tangent of y over x, and our z is our z. So just like cylindrical. Okay, so we're going to identify the surface for each of the following equations. This is in cylindrical. So if r is 5, so if you imagine r equals 5, that is going to look like a cylinder. So the radius is 5, and then z could be anything. Because remember, another way to think of this is x squared plus y squared, the square root of that is 5, because that's what r is. And we're going to get a cylinder, because my cross sections, no, that's right, x squared plus y squared is 5, and that's going to give me x squared plus y squared is 25, which is cross sections perpendicular to the z-axis are going to be circles, and we're going to get this cylinder with a radius of 5, right, sort of going up the z-axis and centered around that z-axis. So this is a cylinder. Centered on the z-axis. All right, if we look at B, r squared plus z squared equals 100. Well, again, r squared is the same as x squared plus y squared, and then plus z squared is 100. And you should recognize that as being a sphere centered at the origin with radius of 10. Right, that should make sense. Right in there. And then finally, if you look at z equals r, again, z is equal to the square root of x squared plus y squared. And this gives me z squared equals x squared plus y squared. And this is different from the first one in that in the first one, our x squared plus y squared was a constant. Here, our x squared plus y squared is our z squared. And if you think back to our contours and or you think of cross sections perpendicular or parallel to the z, to the xy plane, are going to be circles. And basically, these are circles with a radius of z as we go up. And if you think of your contour diagram in the xy, you know, at 1, when z is 1, so my level curve is 1, and then I go, when my z goes up 1, my radius of my circle goes up 1, and so forth. And that constant going out gets us not a paraboloid, but a cone going up, opening up, centered on the z-axis, right, from what we've done before. All right, so now we're going to look at actually changing coordinates from rectangular to polar, polar to or from cylindrical to rectangular. So here I have my cylindrical, and remember this is my r, this is my theta, this is my z. And what I know is that x equals r cosine theta, same as in polar. So that's going to be 2 cosine of 2 pi over 3. And cosine of 2 pi over 3 is negative 1/2, and I get negative 1 for my x coordinate. My y coordinate is r sine theta, which in this case is 2 sine of 2 pi over 3. And sine of 2 pi over 3 is the y coordinate there. It's 2 root 3 over 2. Otherwise, when I simplify that, I get root 3. And then my z coordinate is already there. So my coordinates, so this is my z. So my coordinates in rectangular are negative 1, root 3, 1. And I can go the other direction. It's a little more difficult, but totally doable. So here are my rectangular coordinates, and I want my cylindrical coordinates. And so I'm going to think about the fact that r is the square root of the x squared plus the y squared, square root of 18, or 2 times 9, which gives me 3 root 2. You can also think about just like the xy. Here my x is 3, my y is negative 3, and you should recognize that as the 45, 45, 90 with a scale factor of 3. So that's going to be 3 root 2. And you can also think about this. What is, so I can do either tan inverse of negative 3 over 3, which is tan inverse of negative 1. And hopefully you recognize that as a 45, which is a pi over 4. And then this picture right here with x and y should help you figure out which one, because there are it could be here, it could be, it's not this one up here. So we have multiple options for our theta, but if we actually do tan inverse, we get negative pi over 4, or another name for that could be 7 pi over 4. And so I now have my r, which is 3 root 2. I have my theta, negative pi over 4, and my z again is the same. So in cylindrical, z is the same, and that's an easy conversion. You're not really converting at all. This would also be acceptable, 3 root 2, 7 pi over 4, negative 7. All right. So here we can have an equation in cylindrical. We want to put this equation into cylindrical coordinates. And so cylindrical coordinates, we we know we're in cylindrical when we only have r, theta, and z, right? Some or all of that, but nothing else besides that. So I basically need to get rid of the x's and the y's. The z can stay because that's still a cylindrical coordinate. And so I'm trying to think about a way to switch this. And what I see is that if I factor out my 4, then I recognize that x squared plus y squared is r squared. So this becomes 4r squared plus z squared equals 1. And it doesn't involve theta, which is fine. The rule is to be in cylindrical, I can only use an r or a z or a theta. And this accomplishes that goal. All right, so now here we're going to get a little crazier. We are going spherical coordinates. Yikes. And you can think of it as being a spherical because what I would say is, so we're going to introduce some new letters too. We have a thing called rho, which is actually on this picture, it's right here, but you can't really see it. That's called rho, and we add this phi right there. And so let's look at a little less confusing. So in this case, our point in 3 space is given by a distance from the origin and then 2 angles. And so theta is still the same theta from spherical, or from cylindrical. So theta is still the positive angle from the positive x-axis going towards the y-axis. So it's still this angle right down here. That's still my theta, so that's the same. Then rho, so this guy right here, rho, which is right up here, is the distance from the origin to the point. So one thing we know is that in this case, rho is always going to be greater than or equal to 0. We are not, unlike in polar where the radius can be positive or negative, rho is always going to be positive. And then, so what's left is to figure out phi. So theta is the angle in the xy plane, and phi is the angle from the positive z axis, right up here. So from the positive z-axis down towards the segment that connects the origin and the point. So down to that segment represented, whose magnitude is represented by rho. So it's sort of that angle down. And if you think about this, this angle could go all the way down. If we kept going down to the negative z-axis, the biggest that phi is going to be is pi. And the smallest that it could be is going to be 0. So we're not going to go back that way, because if depending on where we are, we would come this way, because it's a vertical sort of thing. So pi is as big as we're going to get for that. And then we have these relationships over here. So if we think about this, we have this triangle right here. This is a right angle. And because of symmetry, if you imagine this sort of being a parallel line, if you can imagine that sort of parallelogram, since phi is right here, this angle up here will also be phi. And that gives me this right triangle, if you can see it in there. Here's r, here's z, here's phi, and here's rho. Okay? And from that triangle right here, I get that cosine of rho, and you should try this before I write it. What is the cosine of rho? Adjacent over hypotenuse is z over p, or rho, z over rho. So cosine of phi is z over rho, and sine of phi is r over rho. And out of those two equations come these two right here. So we get that r is rho sine phi, and z is rho cosine of phi. Now again, if we use our x equals r sine theta, or r cosine theta, right here, and I replace r with rho sine phi, I get x equals rho sine phi cosine phi. And again, I replace this with r, right? R sine theta, x is, or y is r sine theta. And so I get these relationships right here, which are important in our converting. And rho, the hypotenuse right here is r squared plus z squared. And remember, r squared is x squared plus y squared. So we get this final rho squared is x squared plus y squared plus z squared. And it's a lot, but I think once we start using it, it'll seem a little less confusing. You really have to dive in and try this. So you might want to try this before I do, otherwise you can follow along. So here's my point, and I have to remember, in spherical, this is my rho, that's the distance from the origin to the point. This is my theta, and this is my phi. That's my vertical angle, and theta is my angle in the xy plane to that imaginary sort of radius. All right, I want the rectangular coordinates. So what I know is x is r cosine theta. Oh, but now we know what r is. R is rho sine phi, and then we're going to have cosine theta. Okay. So in this case, I'm going to get x equals rho, which is 2, sine of phi, which is pi over 3, cosine of theta, which is pi over 4. And when I do those out, I get 2, and sine of pi over 3 is root 3 over 2, and cosine of pi over 4 is root 2 over 2, and I end up with root 6 over 2. You can find y in a similar manner. Y is going to be 2 sine of phi, but now it's sine of theta, and that actually turns out to be the same answer because it involves the same cosine of pi over 4 and sine of pi over 4 are the same. And then finally I need my z, and so my z is the one that's a little different. It's 2 cosine of phi, which was pi over 3, and that is 2 times 1/2, or 1. And so my point in rectangular is root 6 over 2, root 6 over 2, 1. All right, one final problem, and then we'll get ready to do some homework. So now I have the rectangular points, and I want to find the spherical. And again, going from rectangular back is a little trickier, but the p is pretty easy, or the rho, sorry. Rho is the square root of x squared plus, plus y squared. So 2 squared is 4, root 3 squared is 3, and then plus z squared. And so this becomes the square root of 16, otherwise known as 4. Now it's generally going to be easier to use the simpler point since I want x, y, z. I'm going to start with the z because that equation was less complicated. Z was rho cosine of phi. And so I know that my z is -2 from my point. I know that rho is 4. And that will help me find phi because I can say that -1/2 is cosine of phi. And again, so I'm thinking -1/2 is here or here, but because phi has to be between 0 and 180, it's not that. And my cosine is 1/2 at 2 pi over 3. Okay, so now I have that, and now I can use either the x point or the y point to get my theta. And I think I'm going to use the x point. If there's a 0, I'm going to use it. So I know that 0, or x, is rho, which was 4, sine of phi, and phi we just found up here, so that's 2 pi over 3, and then cosine of theta. I can divide this, and I get 0 is cosine of theta, and cosine is 0 at pi over 2. And there I have all my things. So I know my rho is 4, my theta is pi over 2, and my phi is 2 pi over 3. There you have it. You should be able to tackle that assignment.